Well, we're ready to talk about MOSFETs. And the first kind of MOSFET that we will talk about is a ballistic MOSFET. Transmission is equal to 1. Now, there actually are field effect transistors that operate near the ballistic limit these days. So this is not just an academic exercise. It's a treatment that applies to devices that can be built today. We're going to call this the transmission theory of the MOSFET because this transmission T plays a central role in what we do. So we have our general current expression. We're going to assume the transmission is 1. So we have a ballistic MOSFET. Any electron that enters from the source leaves from the drain. We'll first of all discuss the linear region, and then we'll discuss the saturation region. Okay, linear region. This is our conventional textbook description that's been around since the 1960s. A key parameter in this description is the mobility, mu sub n, which is related to the mean free path for scattering in a bulk semiconductor or a long channel MOSFET. How does this change for the ballistic MOSFET in which there is no scattering? Well, we have our expression simplified for low voltage between the drain and the source, and we are assuming transmission is equal to 1. Well, we know that our Fermi window was proportional to voltage, so the linear region current is going to be proportional to the drain to source voltage, and we have an expression for that linear region current, and we can simply work it out. I can refer you to the fundamentals of nanotransistors notes to see all of those details. I'll just very quickly indicate how this calculation proceeds. So we're going to evaluate our expression for the conductance of the channel. We know the number of channels in the device. We're assuming the transmission is 1. I'm going to assume non-degenerate Maxwell-Boltzmann statistics, so the Fermi function simplifies. We know that there's a relation between the sheet carrier density per square centimeter and the location of the Fermi level with respect to the bottom of the conduction band, and the constant out front is the effective density of states for the material that the device is comprised of. So we could put all of that into this expression and work out the integral. I'm not going to show you all the math. The reference I just gave works that out for you if you would like to see it. But this is the result. Okay. You'll see that this thermal velocity, this unidirectional thermal velocity that we saw in the previous lecture, and which I said we'll see again and will be important, we're seeing it again. It appears in our result. Also, Q times the sheet electron density, this is just minus the mobile charge in the channel of this MOSFET that we are considering. And we can write that as Cox Vg minus Vt. Okay, so we have an expression for the conductance that we can write. Okay, so that's the result that we've been after. We have now described the linear region current of this ballistic MOSFET. So we've done what we set out to do. We've taken the traditional expression for the linear region current, and we now have the corresponding expression for the linear region current of a ballistic MOSFET. It looks quite different. We'll discuss it a little bit, and we can show you that we can make sense of these terms, and that actually we can make it look very similar to the traditional expression. Now you'll notice that in the ballistic device, it's independent of channel length. You would expect it to be independent of channel length because the longer the channel is, it doesn't make any difference. An electron that comes in from the source is going to go out the drain. There is no scattering, so the channel length plays no role. Okay, all right, so this is our expression. You know, there's a couple of questions that we have. First of all, let's talk a little more about this unidirectional thermal velocity because it's an important velocity, and we'll see it again in the next lecture, and we'll see it again in the lecture after that. So let's talk a little bit about that unidirectional thermal velocity. And the other question that we have is, our ballistic mobility, our ballistic MOSFET expression looks much different than the traditional expression, but the traditional expression seems to work really well. Can we understand why? All right, let's talk about that unidirectional thermal velocity. So remember, in thermal equilibrium, the occupation of the states in the conduction band, if we're talking about an N-channel MOSFET, the occupation of those states is described by a Fermi function. And if we're under non-degenerate conditions, which we're assuming just because it simplifies the math, then that Fermi function can be simplified to an exponential. Remember also that the energy of an electron in the conduction band is the energy at the bottom of the conduction band plus its kinetic energy, which is 1/2 mv squared for a parabolic band. So the result is that these electrons are distributed in velocity space in a Maxwellian distribution of velocities. Okay? So if we look along one direction, the x direction, we'll see a distribution of velocities that looks like this. The overall average velocity is 0 because we're in equilibrium, so the electrons are not flowing anywhere on average. But we have this symmetrical shape about v equals 0. Now, if we look a little more closely, if we just look at the positive half of that symmetrical shape and ask, what is the average x-directed velocity of the electrons that have a velocity in the positive x direction, then we can compute that average. That's what we mean by the unidirectional thermal velocity, and it's given by this fairly simple expression under non-degenerate conditions. It goes as the square root of temperature divided by effective mass. So this is the random thermal motion is coming about because the electrons are being bounced around at random by their interactions with the lattice vibrations. That's where the temperature comes. The higher the temperature, the more the lattice is vibrating and the faster the velocity is. The lighter the electrons are, the faster they go, because 1/2 mv squared is equal to the energy that the electrons have. Okay. Now, what is this? What are these double bracket averages here? Well, first of all, one of the averages is over angle, because in 2 dimensions, the electrons are pointed in various directions. We have to average because we want the average x-directed velocity. When you do that averaging over angle, it's easy to show that the average velocity of those electrons distributed uniformly across those angles is 2 over pi times the magnitude of the velocity. Okay. We also have to average over energy, because these electrons, most of them are near the bottom of the conduction band, but they are spread out over a distance in energy on the order of kT. So we have to produce that we have to do that average over energy. That's what the 2 brackets here mean. One average is over angles to get the average x-directed velocity. The other average is over the energies over which the electrons are distributed. So if you want to see how that calculation goes, I refer you to this reference in the notes, Fundamentals of Nanotransistors. Okay, so let's take a little more look at these 2 expressions. The traditional expression and the expression that comes from transmission theory for the ballistic MOSFET looks quite different, but they're really not that different. So let's take a look at the expression in parentheses and see if we can make sense of it. Well, first of all, you notice the traditional expression has a factor W over L, width of the MOSFET divided by length of the channel out front. So let's divide by length and then let's multiply by length. So we haven't changed our transmission expression. But now when we've done that, if you look at what's in the brackets here, and you ask what are its dimensions are centimeters squared per volt second. All right, that should, ring a bell for us. Centimeters squared per volt second, those are the units of mobility. In fact, let's just define something we will call the ballistic mobility, because we're under ballistic conditions, and this quantity has the dimensions of mobility. we'll call it the ballistic mobility, and we'll see if we can make sense out of it. Now remember our diffusive mobility. We derived this earlier in the previous lecture. And we saw that it was related to the thermal velocity times the mean free path for backscattering. So the diffusive mobility describes the mobility in a material that's very long. We have a corresponding quantity where it looks like we've simply replaced the mean free path for scattering by phonons or ionized impurities or defects or whatever. We've replaced that mean free path for scattering by the channel length of the MOSFET, because there is no scattering now in the MOSFET. So we can easily make sense of that. Remember, our source is a thermal equilibrium reservoir where the strong scattering between electrons and lattice vibrations and other electrons maintains thermal equilibrium conditions. If an electron leaves the source and goes across the channel, across the length of the device, there is no scattering in the device because this is a ballistic device. But when it enters the second contact, immediately it scatters because this is another source of strong scattering. So the average distance between scattering events is the length of the channel. It scatters frequently in the first contact, it zips across the channel without scattering, and then it scatters quickly. The average distance between scattering is the length of the channel. So it makes sense that for this ballistic device, we would replace the mean free path for scattering in a long device with the length of the device, because that's the average distance between scattering events in this short ballistic device. All right, so let's summarize. We could write our linear region current just like the traditional current expression for the linear region of a MOSFET with only one change. We have to replace the mobility of a bulk semiconductor or long channel MOSFET. We have to replace that with the ballistic mobility. And we have a simple expression that tells us how to compute that ballistic mobility. So we can end up making the transmission expression for the linear region current look just like the traditional expression with this definition. In the ballistic limit, the mobility in this expression will be the ballistic mobility. If we have a very long channel length device, then we should use the scattering limited mobility, the conventional mobility. The ballistic limit will occur in very short channel devices, and we do have field effect transistors at this limit in current day technology. The diffusive limit occurs in very long channels. Most silicon technology these days is between these two limits, and we'll have to talk in the next lecture about how we treat that condition. Or in 2 lectures from now, I'm sorry. Okay, we have discussed the linear region current. Let's discuss the saturation region current. We have a simple velocity saturation expression in which Vsat, which is about 10 to the 7th centimeters per second in silicon, higher in other semiconductors, 3-5 semiconductors, for example. But the traditional velocity saturation expression assumes that the velocity saturates because of strong scattering, and it just gets harder to push the electrons any faster. What happens in this ballistic device for which there is no scattering in the device? Well, we'll take the current expression that we had, that we simplified for high bias on contact 2, that made F2 0, and we'll have to work that out under the assumption that the transmission is 1. Then we'll have our expression for the saturation current in a ballistic device. So we are going to be focusing now on the virtual source. And remember, the virtual source is at the top of the energy barrier between the source and the channel. And at that point, the transistor designer works very hard to ensure that the total mobile charge per square centimeter at that point is minus inversion gate capacitance times VGS minus VT. Now let's take a little more close look at what's going on there. So here we'll have our energy versus K plot, our energy versus crystal momentum plot at the virtual source. we have a parabolic band for simplicity. The Fermi level in the source is at some location. The Fermi level in the drain is lower because we're under high VDS conditions. So electrons will hop over that barrier, flow in from the source. They can occupy positive velocity states. The probability that they occupy those states is determined by the Fermi level of the source, because that's where they came from. Now, electrons can also enter the channel from the drain. They have a lower probability of occupying the negative velocity states because the Fermi level is much lower, because the positive drain voltage lowers the Fermi level in the drain. Now, because the drain voltage is considered here to be large, we're under high VDS conditions, we essentially have no probability of occupying negative velocity states at the top of the barrier. Right? The Fermi level in contact to the drain is just too low. So all of the electrons at the top of the barrier are going to have positive velocities. So let's look at that electron density. If I want to compute the density of electrons with positive velocities, I would take my traditional expression and I would divide the effective density of states, n sub 2d, by 2, because only half of the states have positive velocities. And the Fermi level is the Fermi level from the source, because that's where the positive velocity electrons came from. Now, if I ask, well, what is the density of electrons per square centimeter with negative velocities? Well, also, only half of the states have negative velocities, so I divide the effective density of states by 2, and then I occupy those states according to the Fermi level of the drain, or contact to, which is lower by an amount that's determined by VDS. Well, VDS is so large that the number of those negative velocity states is essentially 0. To get the total charge at the virtual source, we add up the electrons with positive velocities and the electrons with negative velocities. There essentially are no electrons with negative velocities, so the total charge at the virtual source under high VDS conditions is all due to electrons that have positive velocities that entered from the source. That total charge is determined by MOS electrostatics, by the gate voltage. So we conclude that the total charge at the top of the barrier is all due to electrons with positive velocities, and it's determined by the gate voltage and gate capacitance through C inversion, VGS minus VT. Okay, so now we can work out the integrals. You know, for the details, I can refer you to the lecture notes on fundamentals of nanoelectronics. We'll just quickly go through how this calculation goes. So we're evaluating our drain current expression, our expression for the current under high VDS. We have an expression for the number of channels. It's essentially proportional to the average velocity in the x direction, the direction of the channel, and the two-dimensional density of states, which is independent of energy. The transmission is assumed to be 1 because we're ballistic. The Fermi function is approximated by non-degenerate conditions, so it's by this exponential. Remember that the unidirectional thermal velocity will come out of this calculation as well. And also, we have to recognize that the electron density under these conditions is given by half the effective density of states, because only the positive velocity states are important under high VDS. Well, if we do the calculation, making sure we account for this factor of 2 here and being careful, we will find that the saturated current is width times Q times the electron density per square centimeter at the virtual source times the unidirectional thermal velocity. That's what the result of performing this integral tell us. We know that Q times the electron density at the virtual source is just given by MOS electrostatics. So putting this all together, we have our expression for the saturated drain current in this ballistic MOSFET. That's what we set out to do, and that's what the calculation from this integration gives us. So we have our result. the saturated current is width times inversion gate capacitance times VGS minus VT times the unidirectional thermal velocity. So we can very simply adapt our traditional velocity saturation model to the ballistic MOSFET by simply replacing the high field saturation velocity for electrons by the unidirectional thermal velocity for electrons. Now I'll just point out that we could actually, or what we've done is to develop an expression for the ballistic linear current and for the ballistic saturated current. It's really quite easy to develop an expression for the entire range of VDS from the linear to the saturated regime. The result is here, assuming non-degenerate statistics, and I can refer you to the lecture notes for details of that calculation. So we can summarize our ballistic MOSFET. In the linear regime, we have a simple expression, looks essentially exactly like the traditional expression, except that we need to use the ballistic mobility instead of the mobility due to scattering. And we have a simple formula for that ballistic mobility, so it's something that we can compute. The saturated current looks exactly like the saturated current in the velocity saturation model, the traditional model, except we've replaced the high field saturation velocity of electrons in bulk silicon by the unidirectional thermal velocity of electrons in silicon. So we have a simple theory for the ballistic MOSFET. Before we continue much on, we should take a closer look at the velocity versus drain voltage at the virtual source, because it's really quite interesting to ask ourselves, how is it that the drain current saturates in this ballistic MOSFET, given that there is no scattering at all? We'll discuss how that drain current saturation occurs in the next lecture.